Alrighty, so here we are with a re-recording of Chapter 4, Section 2, because I decided to rotate the unit circle in the last one, and yeah, that's not good. Okay, so we're going to try this over again. So, evaluating 6 basic trig functions. Now you might think, but I only thought there were 3. Well, it turns out that there are the other 3, which are actually associated with sine, cosine, and tangent, and they're actually the reciprocal of sine, cosine, and tangent. So for instance, this one here is called cosecant, and cosecant is actually equal to 1 over sine, which is why I traditionally write it across from the sine. Okay. The next one is secant, and secant, again, I have written across from cosine because I think of it as associated because it's 1 over cosine. And then the last one is cotangent, and again across from tangent because it is the flip of tangent, which means that it is, well, I gotta write the name, 1 over tangent, but actually more specifically, let's see, tangent is sine over cosine, and so cotangent would be cosine over sine. So, just an interesting relation there. So, the idea here is that we're going back to SOHCAHTOA. And so sine is equal to opposite over hypotenuse. And so we've got our opposite side here, our hypotenuse here, it's across from the 90 degrees, and the adjacent here. And this is only based on the fact that our theta, or where we're standing, happens to be over here. So if we changed to the acute angle that we're looking for being over here, then this would be the opposite side, and this would be adjacent. So these two end up flipping, depending on where it is that you're, what I call standing, but it's where the angle is. Cosine is then adjacent over hypotenuse, and tangent, as the SOHCAHTOA acronym says, is going to be opposite over adjacent. Alright, moving on to cosecant, it's going to be the flip of sine, so you just need your hypotenuse over the opposite. Secant is going to be the flip of cosine, so it's hypotenuse over adjacent. And then our cotangent is going to be the flip of tangent, so adjacent over opposite. Alright, so those are our 6 basic trig functions. So anytime they're talking about evaluate the trig functions or find all of them, which is what the next one is going to be, that is what we're going to do. So this one doesn't have directions, but it's actually the same as here. Find the values of the other trig functions. So find trig values. So I tend to write these in the same way as was presented. So I write them so that I can see sine first, and then its opposite or its flip, cosecant. And then I write cosine, and then its flip, just so that I can have the visual that it's going to be the flip of it. And then tangent, as well as cotangent. Just to reference, this is not on your calculator as any certain button, and so you will always have to, in your calculator, have to do 1 over sine, and so it will never be this other button. The sine inverse is actually what we're going to talk about later, so that's not cosecant. Alright, so we're going to find the trig values. There's something missing because we have where we're standing, and then this is our opposite, and this is our adjacent, but we don't have our hypotenuse. So how do we find the hypotenuse? We need to realize that this is going to be our A value, this could be a B, and this could be a C in the Pythagorean theorem. So in order to find our hypotenuse, our A value is 7, we'll add that to our B value, which is 11, and then it's going to equal C squared. So 49 plus 121 is going to equal C squared. And so we have 170. If you can simplify 170 or reduce it, that's fine. But the idea is that we would not end up giving the decimal of this, because a decimal in a fraction is very weird. So it's like a fraction in a fraction. so it's just not necessary. So our hypotenuse is actually the square root of 170. So as we look at giving our ratios for all of these pieces here, if we start with sine and SOHCAHTOA, sine is going to be opposite over hypotenuse, so 7 over the hypotenuse that we just got, which was square root of 170. The cosecant over here is going to be the flip of that, so you can always just take the time to right away rewrite it flipped. The cosine is adjacent over hypotenuse, and so that's going to be 6 over the square root of 170. And then secant, of course, is the flip of that, so 170 over 6. And then the tangent is opposite over adjacent, so 7 over 11, and then, of course, cotangent is the flip, so 11 over 7. Pretty much all of these are going to make it so that one of the pieces are missing, and so you are going to end up having to use Pythagorean theorem a lot. So this next one doesn't give us a visual, so darn it, we have to find our own. So if we pretend that our theta is here, sine is opposite over hypotenuse. And so if our opposite side is 3 and our hypotenuse is 5, that actually means by a special right triangle, or what is it, Pythagorean triple. There's also a 5, 12, 13 Pythagorean triple. There are a few of them that show up. So other than knowing by a Pythagorean triple that that's 4, we could also actually do the fact that this might be C, this could be A, and what we don't know could be B. And so we could do the Pythagorean theorem and come up with 4 either way. So 9 plus b squared is 25. Subtract out a 9, and get a b squared of 16, but of course then a b of 4. So either way. Then we can list out all of our trig functions. So we've got sine of theta, and then its flip, cosecant. Whoops, apparently I'm really into writing s's. Alright, we also have cosine and its flip, which is secant, and then tangent and its flip. Alright, so sine is opposite over hypotenuse, so here we are with opposite. This one's hypotenuse, this one's adjacent. And so sine, of course, they gave us to begin with, and so it's 3/5. Cosecant then is the flip of that, 5/3. Cosine is adjacent over hypotenuse, so 4 over 5. And then, of course, the flip for secant. And then tangent is opposite over adjacent, so 3/4. And then the flip 4/3. We don't ever actually make these into the decimals, so please don't do that. Especially because if we decided to tell you that sine of theta was 0.6, it's probably a lot harder to see that that is a fraction and therefore could be applied in the way that we just did. So we don't want to do decimals because it ends up making it hard to apply to this idea of a triangle with opposite and adjacent sides and such. Alright, so the next thing we're going to do is kind of talk about the unit circle, and of course this is what I got wrong on the first video, mainly because, hey, clockwise makes sense. Turns out that 0 actually starts here and then rotates around this way. And what I did in the video is actually had 0 start here and rotated this way, so I'm really sad that I did that. Then I looked online and was like, why are all of these rotated? And did it change? I was actually going to call my friend and be like, did I miss something new when we decided to orient the unit circle differently? So, anyway, annoyed. That's because most of what we start with is here, so that we can kind of apply triangles to the origin as much as possible. And so it was just annoying that I didn't remember that, and now have to redo the video. So, first thing that we're going to talk about in filling in the unit circle, and I have kind of a bigger one here to fill in, is about our degree measures. So, as we look at this circle, as I mentioned earlier, this is 0 degrees. If you rotate to this next piece up here, it does go, as I mentioned earlier, counterclockwise. And so that means that we are going around the circle in this backwards, well, it's going to feel backwards direction because of the normal clockwise that we think of things. So 0 degrees is there, 90 is rotated over here. We also have then 180 this way, and then 270. So these are very common measurements, and then it turns out that 360 would be back here. So if you ever get to that one, that is the next one. After that, we do have the median angles. So for instance, this is 45 degrees after 0. And then you'll notice that this is off-center a little bit, and that's because if we did put all of the tick marks in here, we would end up actually having 15-degree increments. We will go over the reasoning for the skipping of these increments when we go over the radians, but we are skipping 15 degrees and then also 75 degrees. So if you feel like filling them in, that's cool, but the idea is that we don't have those pieces in here. So then the next piece we'll skip from 90, adding 30, so we're going to have 120, add another 15, so 135, add another 15, and so 150, and then add a 30 to get 180. Continuing on, we'll add a 30 to get 210, add 15 to get 225, add 15 to get 240, and then add 30 to get 270. Add another 30 to get 300, and then 315, and then 330, whoops, and then 360. So those are our degrees. Pretty much something that, as long as you know that we start at this base here, that is going to be 0 rotating around. Alright, so then we talk about radians, and radians are basically another way of looking at a circle rather than degrees. The interesting part about radians is that it's not an entire rotation that makes a pi, it's actually only one rotation. So, or sorry, half a rotation. So I feel like radians actually make it so you can be more precise than degrees, but also at the same time degrees can be broken into 360 pieces and pi is pi. So anyway, doesn't really matter. So if pi is all the way over here, 0 of course is going to be here, and then halfway between it, very easily enough, is going to be pi over 2. So it's a fraction. Okay. After that, if we were talking about a half of a half, we actually have pi over 4 here. But before we get too into that, I'm actually going to talk about each of these pieces, and that's why all these red lines are here. So, if I talk about this entire thing as being a pi, there are actually 12 pieces, if we include the pieces that I talked about not including. There are 12 pieces. And so this is where we get to the reasoning of why we don't have these two lines here. So, for instance, this piece right here would have been pi over 12. Alright, after that it would have been 2 pi over 12. Then we would have had 3 pi over 12, 4 pi over 12, 5 pi over 12, and 6 pi over 12. So the reasons I'm writing them out here is because I'm actually going to simplify them. So 2 pi over 12, the reason we keep that is because we can actually reduce that by dividing the top and bottom by 2 and getting pi over 6. After that, if we divide the top and bottom by 3, we're going to get pi over 4. And then if we reduce, we're going to get pi over 3. And then, of course, reducing 6 pi over 12 is pi over 2. So, the reason that we skip this one and continuing on is actually because they do not reduce with 12 evenly. And that is literally it. So, our key pieces of radians that we are going to keep are all of the ones that end up actually dividing out with 12 the best. So, numbers like 3 and 4 and 6 and 2. Alright, if we continue on with this process, remember this was 6 pi over 12. This piece here would have been 7 pi over 12. Again, 7 is prime, not going to go into 12, so we skip it. 8 pi over 12, 9 pi over 12, 10 pi over 12, 11 pi over 12, and then 12 pi over 12. So if we simplify that, again, 7 pi over 12 doesn't reduce evenly, so we're going to cancel that one from being in our memory. The next one is 8 pi over 12, which we'll divide by 4, and so we get 2 pi over, nope, not dividing by 4, yeah, dividing by 4, so 2 pi over 3, hello. The next one, dividing by 3, gets you 3 pi over 12, which is 4, dividing by 3. Divide by 2, we get 5 pi over 6, and then of course 12 pi over 12 reduces the 12s. Alright, then continuing on our pi's, on our radians, turns out if we go all the way around, we're going to end up with 2 pi. Alright, so 2 pi is going to be an entire circle versus just 1 pi. It's something that people tend to forget. So an entire circle is 2 pi and not just pi. One thing you'll notice in this is that other than noting that there are parts of 12, you also see that hopefully the denominators have this pattern. 6, 4, 3, and then a 2, and then 3, 4, 6. So it turns out that that will mirror down here as well. The base here will be 6, then 4, then 3, then a base of 2 for our radian, 3, 4, and 6. So those will repeat. The first circle, the first quadrant, which is what we are pretty used to having, is going to be all just pi over. Then it's 2, 3, 5 for this pattern, so it's really not all that helpful. And then I believe it's 5, 7, 11 for this one, but now I can't remember, so we can just continue on our pi's. This would be 13 pi over 12, again doesn't reduce nicely. 14 pi over 12, 15 pi over 12, and 16 pi over 12. 17 pi over 12, which definitely wouldn't reduce very nicely, and 18 pi over 12. So if we simplify, 14 pi over 12 definitely divides in half, so 7 pi over 6. Then we have 15 pi over 12, and so that's going to divide by 3, so we get 5 pi over 4. And then 16 divided by 4 makes 4 pi over 3. And then over here, let's see, we'll divide by 6, so 3 pi over 2. Alright, after that we continue on with our pi's. We've got 19 after this. So 19 pi over 12, which of course is not going to reduce. 20 pi over 12, 21 pi over 12, 22 pi over 12, and then we can stop because it would be 23 and 24, which 24 we already know is 2 pi. Alright, so reducing 20 pi over 12, that means that we can reduce them in half. Oh, and then in half again, so it looks like 5 pi over 3. Then we'll have 21 divided by 3 and 12 divided by 3, so 7 pi over 4, and then dividing by 2 in the next one, so 11 pi over 6. So that's our pattern. Again, it's all about breaking it into that first half of 12 pieces in the pi. What happens with radians is that people will use them more often than degrees when we're presented a problem. And so, for instance, actually up until more recently, I pretty much only referenced radians because that's usually what was given. But most people now just kind of transfer to degrees. So you'll get a problem in radians, convert it into degrees, and then usually give your answer in degrees. But it's also always nice to give your answer in whatever format the question was given. So if they ask you, in how many radians would this be, you can do the whole work in degrees, that's fine, but then convert your answer into radians. Alright, so the next thing that we're going to talk about is these coordinates that are out here. And these coordinates actually come from sine and cosine. So cosine is actually what we would traditionally call the x value, and sine is actually going to be what we would traditionally call the y value. So, for instance, if I want to find this value right here, I'm going to get this value, which is the x value, if I take the cosine of 30 degrees or pi over 6. If you do that on your calculator, you are going to get a decimal, and the only 3 decimals other than 0 and 1 that you're ever going to use are a half, square root of 2 over 2, and square root of 3 over 2. This is the least value that you'll be given, 0.5, and this is the greatest value. And so you can either have those memorized if you want to do it on your calculator continually, or you can actually use this idea of this being a grid. So we're going to look at this image and we are going to associate it with being on a piece of grid paper. So right here in the middle would be 0, 0. And so if I want to, for instance, get to this coordinate out here, I'm going to go over 1, because the unit circle has 1 unit as its radius. Who knew? So we're going to go over 1 and up nothing to get to it. And so that's the coordinate of that point, if you will. If I want to kind of use that, basically I'm saying that sine of 360 degrees is, well, sine is the y value, so 0. So the idea is that you can take the sine, cosine, and even tangent, if you do a fraction, of each of these stopping points here, and know its answer by looking at this coordinate. So on that note, if we are going to pretend that we are going for this coordinate up here, we are going to go over what seems like quite a bit, and up what actually seems like a littler amount. And so looking at our options of what we have, if we're going over the large amount, that means that we're going over square root of 3 over 2, because that's a larger one, and then up the smaller amount, and so that's a half. The next one is going to be both over and up that same mid amount, and that mid value is the square root of 2 over 2. And then the last one, again, if you're trying to get to this coordinate, you're going over a small amount and up the largest amount. And so you're going to go over a half and up square root of 3 over 2. Then going back to being on the axis itself, we have a radius of 1. So we're going over none and up 1, which again means that the sine of pi over 2, for instance, is 1, because that's its y value. Alright, moving on, the second piece, we're going to get to this dot right here, and how do we get to that dot? We go over a small amount and up the largest amount. So we're going to go over negative a half and up square root of 3 over 2. Again, if this is 0, 0, to get to this point over here, we're going backwards, square root of 2, that middle range, and then up square root of 2 over 2. Getting to 5 pi over 6, we're going to have to go left the square root of 3 over 2, the larger amount, and up the smaller amount. And then back on this main area here, we have a radius of 1, and so negative 1, and then up nothing. So it continues on in that fashion, and again, the reason that this was wrong to begin with was because I decided to put 0 here and then rotate this way. It was a mess, so please do not look at that video. I'll delete it in a little bit. So the next one is going left square root of 3 over 2. You may notice that these x values are going to be repeated down here because of the fact that you're going left that certain amount. And then now we're going down as well, so negative a half down that small amount. Then we're going left square root of 2 over 2 and down square root of 2 over 2. Then left a small amount, so left or negative 1/2. And then down negative square root of 3 over 2. Last one on an axis here is going to be down 1 and over nothing. And that's actually the wrong way, over nothing and down 1. It's over first, then down. And then our last one, which would have positive x values, so over a half and down square root of 3 over 2, over square root of 2 over 2, and down square root of 2 over 2, and then over square root of 3 over 2, and down a half. So that's how we are reading the unit circle and how you can use it. So you can apply it to a problem, for instance, what is the sine of, or let's go with cosine. What's the cosine of 3 pi over 4? Cosine is the x value, so it's negative square root of 2 over 2. Which again, your calculator will give you as a decimal, but not in relation to the unit circle. Alright, there's also a formula sheet that you can use. So this formula sheet has all of this filled in a much better handwriting than mine if you want to take a look at that, and of course use that on any test or quiz or assignment. So, without using a calculator, we're going to go ahead, as in using the unit circle, and find sine of 270. So sine of 270 goes down to this here. Sine is your y value, and so sine of 270 is negative 1. Then we have tangent of 30, so going over here, tangent of 30 gives us a coordinate of square root of 3 over 2 and 1 over 2. And so that's telling me that the cosine is square root of 3 over 2, the sine is 1 over 2, and remember that tangent is sine over cosine. So if we simplify, that means that we're looking for sine of 30, which is a half, and cosine of 30, which is square root of 3 over 2. And if we multiply by our reciprocal, so that we can solve, we cancel our 2's and realize we have 1 over square root of 3. So tangent of 30 is 1 over square root of 3. And again, that would have been given as a weird decimal, so instead we want to use it in the unit circle. The next one here asks us backwards now, so it's saying if you have cosine that ends up being negative square root of 2 over 2, meaning the x value, what degrees might you have? So if you want an x value of negative square root of 2 over 2, that's going to be this one here and this one here. So we're going to end up saying 135 or 225. And what happens is when you get one of these questions, which you will on the test, or sorry, on the assignment, it will say something like, give me the acute angle, or give me the angle between 0 and 180, or the, so it will restrict it. It might also talk about a quadrant, and so just so that we're aware, this quadrant up here is 1, this one is 2, this is quadrant 3, and then this last one is quadrant 4. So just so that we have that reference, as it might indicate that. And then the last one is asking cosecant of negative 2. So cosecant of negative 2 means that we're actually doing 1 over sine, and that is going to be negative 2. But remember that it's the inverse here, and so if we flip, we're actually looking for when is the sine negative a half. And of course the sine is the x value, and so we go back and we try to find one that has, a y value. That is just bad, okay. And so we go for a y value of negative a half, and a y value of negative a half is going to be down here, and then also over here. So 210 and 330. And again, it will be more specific in an assignment which one, or maybe it will say list all. The last ones here just use regular trig, and so all we would do is say that we are standing here and we are trying to find the hypotenuse. So we'll use the opposite and the hypotenuse in SOHCAHTOA. And so we'll set it up as sine of 34 equals opposite over hypotenuse. And so sine of 34 equals an opposite of 15 over x. Solve that with a proportion, meaning we're going to do 15 times 1 divided by sine of 34. Make sure you're in a mode of degrees because we are inserting 34 degrees, and so from that we have an x value of 26.82 degrees. And by degrees I don't mean degrees, because it's a length of a hypotenuse. The next one, just kind of quickly, because we only get 30 minutes. So we'd set it up like this, set it up as a proportion, so we'd end up doing 14 times sine of 43 over 1 to get our x. Leaves us with 9.55 for that length. There we go. Done.